Okay, today I'm going to present several works we are doing in the last, we have been doing in the last years in my team related to the use of synthetic data. As you know, in the last decade, even a bit before, it has been a growth in the use of synthetic data for computer vision in general, and in particular for autonomous driving. We were on that more than 10 years ago. At the beginning, the work was to convince people to use synthetic data to do this. Now this is super clear. Then later it was to convince people to work on domain adaptation. Now this is super clear that it has to be done, and so on and so forth. And in this path, in our lab, probably you know Cynthia dataset that has been used a lot for domain annotation. And in the last years, the CARLA simulator, which is something we do in collaboration with Intel Labs. So in this path, what was clear for us many years ago is that we don't want to be labeling. I remember a project we did on controlling headlamps for a company, and we had to label like 100K blobs at nighttime images, which was super painful, and it was super clear that we didn't want to do this more. So we said something like, okay, we are coming from the Computer Vision Center in Barcelona, so we have to focus on cameras, and let's do things or approaches, procedures, whatever, that allows us to minimize labeling effort. And one of the first things was to use synthetic data, obviously. But other things are just to go for approaches that don't need labels, which then you remove the problem from the beginning. And the talk of today is covering a bit what we have done in these topics in the last years. So let's start with the first thing. Let me start by presenting UrbanSynth, which is a new data set that hopefully is going to replace Cynthia. And this is the team that have been working to create it. People from the University of A Coruña in the northwest of Spain. We are in the northeast, and also with the collaboration of Intel. So this work started with a previous work that we were doing on domain adaptation about one method called co-training. And in this work, we were dealing with semantic segmentation. Previously was object detection. But the point was that it was super clear that we should combine synthetic data sets to get more diversity rather than using one by one of the data sets that are available, like GTA, Cynthia, Senscapes. If you combine them, you are going to have a stronger baselines. And I'm particularly interested in always starting with a strong baselines, because otherwise you can be like producing illusory gains in the field. So after looking at these results, we thought that, okay, it's clear, we have to combine baselines. But on the other hand, when we were combining GTA 5 and cityscapes to do domain adaptation to cityscapes and mapillary and BDD, it was clear that our Cynthia dataset was not adding more value to GTA 5 and cityscapes at that point. So we decided to go for a new one. And what we did was to design different ODDs, with the hope that they will be producing, or they will help us to produce images that were different enough from GTA 5 and from Senscapes. So we were not particularly adapting this dataset to any real-world dataset, just were inspired in some streets around Barcelona or around European cities, and also we were like incorporating maybe in one street traffic signs that are from the US, or in another street from Europe. We didn't care too much because this was for static images. So also, we were not like generating many images. We were generating 7K because we wanted to keep it compact. You know, in the academia, we don't have a lot of computational power, so we need to run experiments. We have to think well what we are going to do. And the point is that this dataset is based on physically based image rendering, so these are photorealistic images. You have here a video how we create the environment is done by layers. So first of all, static infrastructure, later dynamic objects, and so on. And then we can vary the lighting and all these things to generate these combinations of images. At this point, we were guessing that this will be complementary to what already exists. So we were not totally sure, but there were evidences with real world data sets in semantic segmentation, monocular depth estimation, and object detection that when you combine these real world data sets from different sources, the results were improving. So we were hoping that this will be also the case here. Okay, so I think we can see here, not super well, but different, the same scenario, for instance, taken from the same camera location, but where we have changed things like the color of the assets, the road surface from traditional asphalt surface to more stone-like surface, the number of cars that are in the scenario, and so on and so forth. And in here you can see other kind of pictures where we were taking images in, let's say, streets that resemble some places of Barcelona, with roundabouts, with some narrow roads, and so on and so forth. But we were also incorporating things that are more, let's say, different from the previous ones, like more open areas in terms of number of lanes, with buildings that are not Barcelona style and things like that. Okay, then what happens with the numbers when we use this data set to do semantic segmentation? The numbers are these ones here. As you can see, where when we use our data set urban scene with different architectures like segformer or DeepLab v3 in different target domains, cityscapes, PDD, Bapillary. In isolation, our dataset is providing better MAU performances than the other, even it's smaller. I think that if I check with the previous talk, the numbers, some of them are better than the numbers produced by some domain adaptation techniques. This means that the urban scene dataset is good enough, in our opinion, but the most important thing is that when you combine it with GTA and scenescapes, you have amazing performance, because, for instance, if the reference for segformer is 81 MAU, we get 70 in cityscapes. For DeepLab v3, we go to 68 when the reference is 79, and you can see more or less the same pattern for the other data sets. And this is without any domain adaptation. But we wanted to be sure that our baseline, meaning only using the data set, the synthetic data sets, this baseline is high enough, because then the challenge is higher. The challenge of this last mile to get the reference is harder. And then we applied some domain adaptation techniques, because we wanted to be sure that when you apply the domain adaptation, it actually can benefit from this data set. And we saw that, for instance, this morning, the HRDA was explained by the author, so we use it without the this ImageNet feature distance feature, because we wanted to see the effect of the pure dataset, synthetic dataset. And we see that we are almost there. For instance, in cityscapes with HRDA, we reach 76 from the baseline of 70, and the reference is 81. For when we go for the Deep Lab V3 architecture, we use co-training instead of HRDA, and we get a 75 coming from a 68, and the reference is 79. So this is repeated with BDD and Mapillary. So we see that actually this 7K data sets that we are going to, by the way, put free for research is providing value. And we hope is going to be used for synth to real domain adaptation in the near future. Okay, next thing. In the last 2 years, we were focusing quite a lot in a project about autonomous driving in the Pyrenees, so in the mountains. And we have to contact a big team, and this is a team of CVC people. The point of this project is that it's a very tricky area. It's an area where there is no mobile coverage. The road is with asphalt, but with many patches. There is one single lane to go and return, so not 2 lanes, just one. If you cross with another car, you have to do tricky things to continue. And there are pedestrians, vehicles, animals. It can be sudden adverse weather conditions. The trees are perennial trees, so the leaves are in the road in half an hour in the autumn. Eventually, a lot of debris, and so on. So this is a really narrow road. This is my car, and you can see how close is the car to the border of the road. And downhill to the road, you get there. You find the river 50 or 100 meters above. So it's challenging. So the maximum speed that we were targeting was 20 kilometers per hour for this project. So what we did was, from the 4.5 kilometers that we have to cover, we selected 800 meters to do training and testing. The other would be for generalization. It was tricky because even using Google Maps, we were aware that the road that you can see in the Google Maps is not really exactly what you get there. It was missing a bridge, which is a very hard curve that have to be taken into account. The point is that in these 800, 700 meters, we were putting a RTK system also, because we wanted to train an imitation learning based part of the whole system. And for that, we needed waypoints for supervision. For the rest of the trajectory, we don't have any kind of RTK coverage. So we were using a car from a EU project that was provided by Seat and Volkswagen. We were insisting them to borrow the car, and they were at the end happy to share it with us. So at the CVC, we don't have the capacity of robotizing cars. So we need that someone from the industry help us with that. And yeah, at the end, we got e-Golf, which is robotized and sensorized. It has many sensors, but we were using only the cameras, one camera, by the way, and one radar. At the end, we were focusing on moving forward, since there is no way of turn in these roads. You have to keep going forward, no other possibility. So the point here, and what is related to the synthetic data, is that in the schedule of the project was like 2 years. But the physical car was, in theory, was not able to be with us until, let's say, the last 4, 5, if we were lucky, 6 months. So this means that we couldn't wait to do everything in this time. We needed to do everything before, or as much as possible before. And for that, what we decided is to do a sort of digital twin with CARLA. This was the very first version of this area in CARLA, where we were focusing just in having the road in place. And with that, the people working in planning and control actually could start to work on that part, because it's not, you can assume that the perception is given. Some areas like this one were very dangerous, as you can see. With the trees is another thing, but without the trees, you see the real danger. Okay, and this was already when we finished the whole thing, and we put the trees, the proper materials, everything. In here there is a fence, because someone promised us that it will be a fence, but this never happened, so it's only in the simulator. But the point is that with this, we were in the position of doing the full stack development, and then wait until having the car and just move everything that we did in the simulator to the car. In here, I'm not talking about domain adaptation. I'm talking about all the decisions that we made, whether this network or this other, whether this flow of things or this other, all these kind of decisions were already done in CARLA. And I think we didn't touch that much once we started to do the real test. So I can skip this. This is the kind of information that we have in CARLA in the area that we selected for training and testing. You see the semantic segmentation, the depth, and one thing that you have in CARLA but we didn't have in the car is the third person view. And this is more important than it seems, because when you are the safety driver in these very narrow roads, you don't see the limit. And there is always this point of, okay, should I leave the autonomous system continue or should I correct? It's not, if I would have a third person view, like from the top, it could be much easier to decide, but from the driver position, it's very hard to decide sometimes. So basically, in terms of solution, we were focusing on an image-based solution where we have semantic segmentation, monocular depth estimation, object detection, and all this is combined in a bird's eye view. We use LiDAR, but just in training time for training the monocular depth estimation. In testing time, we needed to add radar in the last moment because someone did something in the road that was not, let's say, the best idea. And then we have to incorporate radar in a hurry to the bird's eye view. But the point, the interesting thing here is that in this bird's eye view, what we were doing is to come up with a path of waypoints that is the path that the vehicle should follow. And we did it in 2 different ways. One way was traditional, like engineering, some algorithms where you have the road borders and then you try to kind of compute the middle of the road. And the other way was to use imitation learning. So since we were driving in these 700 meters and we have RTK information, we knew in the bird's eye view the path that the car was following in terms of coordinates. So we could train an imitation learning method. And this was important because you cannot assume that in every single time step you are going to have a good semantic segmentation, a good monocular depth estimation. It's not possible. Even one of the things that we have to do is to use a bit not that good models, but faster, because we needed to go fast, providing decisions or giving commands to the car to avoid that this command is coming too late and doesn't make sense anymore. So this is basically what we did. We use a ROS2 layer to talk either with CARLA or with the car, but from the point of view of the AI that we were developing, it was no difference. Okay, so here you see the graphical interface that we were using in CARLA, which is exactly the same that we were using later in the real car. The point here is that we were using a scenario runner to generate hundreds of scenarios. And then we were able to, during the development, we were able to check where the system was failing. And then we went to the failure case and say, okay, what is happening here? Why is failing here? And then this was very, very important. So let's say that in an automatized way, once we did the proper code, we were able to, generate all these cases. Okay, here, this was the plan, as I said before. Later in real life, nothing of the plan was almost happening. We have a lot of animals in the middle of the road because at that time, there are a lot in this kind of road because they move from the higher part of the mountains to the lower part. We were supposed to have a charger for the car, but the charger came after the project and things like that. I mean, very crazy. But at the end, we make it. These are some examples from the real car. You can see that the semantic segmentation is not always perfect, but still we are able to keep the car in the right path. And in here you can see some autonomous driving. In here you push with 2 fingers at the same time, 2 buttons of the steering wheel, and then the car starts. And then you can keep yourself very close to the steering wheel, just in case you have to correct. Because as I said in here, the problem is that you don't really see I didn't see the road border. It was kind of feeling more than seeing. And then you have to be very close to the car in the generalization areas. In here, not, because this is a training area. And then you are sure that everything is working super well. But in the others, you have to be more careful. Also in adverse weather conditions, like here. With snow, we didn't train anything with snow. CARLA don't have snow. And this was the last part of the project. So before we didn't even have images with snow. So still it was working well. Also, it was possible to, up to some extent, to work at nighttime because the lights of the car were good enough. And the most difficult thing is that at the end, we decided to try also in non-asphalt roads. So we put the car just in this kind of road that you can see, plenty of bumps and potholes and things like that. The problem here was that as I said, the maximum speed is 20, and we were not able to detect potholes as such. So if it was a straight road with potholes, the car was going at 20. It doesn't matter if. So we were like a bit crazy driving, having a bit of crazy driving. Okay, this was relying on CARLA. And what lessons we learned? For instance, one thing that we have to improve in CARLA is modeling the fisheye cameras. This was not done at that time that we were doing that project, and it was a bit of annoying. Another thing is to account for the latency of your system in the simulation. I mean, you take the raw data, the images, you process, and then you deliver the commands to the car. And this takes some time and has to be modeled in the whole system. What else? The imitation learning was working better than handcrafted the algorithms to know the middle of the road. And sometimes it was much better to use models that will not be published because the performance is lower, but they are faster. And then it means that you can use them and it works. And with the others that the performance is better, they are so slow that you cannot use them. So this is not usually taken into account or not always taken into account when we read these many papers. Okay, then moving to another thing, still with the CARLA simulator, something that you can read in new papers on end-to-end driving, meaning that you don't label anything, is you put the images in your model and then you get the commands, the steering angle and the acceleration. There are many new models and all of them are performing much better than one model that we put there some years ago, which is the conditional imitation learning. And of course, the problem of that is that when you look at these tables and you are not really expert, you are starting, it may look like the pure vision-based approach is not worth to be pursued. But the only thing that happens is that this model was done 5 years ago. And there are things that we know now that should be incorporated. And again, I'm very, always very concerned about having a strong baselines. And then we decided to upgrade our conditional imitation model with very basic things, which are, on the one hand, to use a field of view, horizontal field of view that look like the human driving. This avoids some types of causal confusion, because sometimes if your field of view is very narrow, the car is stopping because there is a red traffic sign, but you don't see it in the image. So there is no way that the system understands that, because this is a frame by frame model. So we are not processing several frames at the same time. We are not using any temporal coherence, any of these. So this was one thing. Another thing is that if you use the default driving expert of CARLA is a bit systematic, is too much perfect. And then this may be problematic because your data lack diversity. And then we use the RODS expert, which was developed after the conditional imitation learning to collect data. Also, we incorporate an attention mechanism to the conditional imitation learning. So after all the convolutional layers based on a ResNet, we were using an attention mechanism. And we incorporated also additional commands because when we did this conditional imitation learning, only the town 1 and town 2 and maybe town 3, I don't remember, of CARLA were there, but these were single lane cities. And now we have multi-lane cities. So we needed to incorporate things like lane changing. With all this, where the wider field of view was done by just using 3 cameras, we trained a new conditional imitation learning system that we call it ++. And we compared it with the state of the art at that moment, which is called MILE. This MILE is using bird's eye views with semantic segmentation as supervision, so much more supervision that we have because we don't have any kind of pixel level information, just the steering angle and the speed and the acceleration and all this as supervision. So we are worse than mile, but not that far. And the point is that, as we will see in a moment, we have been able to move our conditional limitation learning plus to a real car because we didn't need to annotate any data, just drive. And for the other, we will need to collect the bird's eye views, labeling somehow this, I don't say necessarily by hand, maybe by using some semantic segmentation method that is good enough. I don't know. But it's not direct to use this mile or others. And yeah, the point is that, again, here we need to compare methods, not only in terms of absolute performance in driving, but also taking into account what is the sensor suite that they need in training and testing, because otherwise you get to very unfair comparisons. Okay, so this is the kind of thing that in CARLA we can do. Stopping for pedestrian, this was already possible, but now in multi-lanes, and the same for vehicles, this was already possible before, but again, in multi-lanes. Okay, and so on and so forth. I think that many of these things were already possible, but now they are possible robustly in multi-lane towns, and also the performance is much better than before. But the point here is that we took this model and the car of the previous project, and we said, okay, let's use the 3 cameras that are in this car. This car has in the windshield 2 cameras, one with 120 degrees, the other with 60. And in the bottom, in the logo of Volkswagen, it has a camera with, I think it's 180 degrees. I don't remember exactly. These are 3 cameras, which are very different of the cameras that we put in CARLA, that were basically to have a continuous horizontal field of view, which is, I think, 180 degrees or something like that. Okay, then you can see here the actual driving in the campus of the UAV. In this case, you can see how in this place we take to the left, but before it was to the right, just because the command was different. In here we go to the right because we give the proper command to go to the right, and the same place now to the left. In here to the right, and we keep to the right. These are the kind of commands that we give to the conditional imitation learning method. In here, in the same place, we say keep going straight, not to the right, and we go straight. In here, there is a bus in the middle, but we have to go right anyway. Doesn't matter that there is a bus. We have to go through the small, narrow path. In here, roundabouts. Roundabouts are a bit nightmare many times. In here, we keep going inside the roundabout until we say something like go to the right. Like here, sometimes, of course, you find also some car parked in the roundabout, and the car have to correct for that. In this case, I have to say that the maximum speed is 30 kilometers per hour. And this has been trained on, I think, 20 hours of driving. Yeah, this is the last thing, yeah. So we are finishing. I think I can, let's see how much is missing. Okay, these are more examples here. We are advancing some cars inside the roundabout. And we will see also some interaction with pedestrians coming soon. And this is the last thing. I'm sorry, I lost the time. Yeah, these are more crazy roundabouts, which are especially difficult many times. Sometimes they are very small, and it's not easy to skip them. And here we can see how the car start to orientate itself to skip pedestrians, not in the last moment, but from the very beginning. So this is an area where pedestrians and cars, let's say, move together to go to the station in the UAB campus. And the point here is that in these models, we don't have an explicit concept about what is a pedestrian, what is a car, what is whatever. It's just pure end-to-end driving from the images. So I think that this shows that these models have been a bit underestimated in the last years, and they can do more than it may look like. And with this, I finish.